We're going to take a look at the loop of Henle in juxtamedullary nephrons. So the loop of Henle in the juxtamedullary nephrons has a descending limb, which is going to go down deep into the renal medulla, and then the ascending limb is going to come back up towards the renal cortex and then turn into the distal convoluted tubule. The descending and ascending limbs are very different in what they're permeable to, so they're just the opposite. So the descending limb going down is permeable to water but not solutes, and the ascending limb coming back up is permeable to solutes but not water. And because of this arrangement, this is going to create the medullary osmotic gradient that's in the renal medulla, and that's going to be necessary for concentrating the urine in the distal convoluted tubule and the collecting duct. So we call the loop of Henle in the juxtamedullary nephrons the countercurrent multiplier, and we'll show you why that is in another picture. So the osmolarity near the renal cortex is going to be lower, but as you go deeper down into the renal medulla, the osmolarity gets higher and higher. So the osmolarity is just the concentration of the solute particles. And this is going to create the gradient that we need to reabsorb water in the distal convoluted tubule and the collecting duct. And we're also going to use some urea and also some other solutes to create this medullary osmotic gradient. Here's what the medullary osmotic gradient looks like. So up here on the top, we've got the renal cortex, and notice that the osmolarity is 300 milliosmolar. And then as you go further down the renal medulla towards the renal pelvis, notice that the osmolarity gets higher and higher. So this is the medullary osmotic gradient, and this is going to be created by the loop of Henle in these juxtamedullary nephrons. And this is what we need to concentrate the urine when we get to the distal convoluted tubule and collecting duct. And then also in this picture you can see the different permeabilities. So the descending limb of the loop of Henle going down is permeable to water but not solutes. And then the ascending limb is permeable to solutes but not water. So let's take a look at the ascending limb of the loop of Henle first. So we're going to look at a picture to show you this. So where we are, we have our proximal convoluted tubule up here on top in the renal cortex. And then you can see our loop of Henle going down. Here's our descending limb going down into the renal medulla. And then our ascending limb is going to come back up towards the renal cortex. So we're going to look at this ascending limb first. So the ascending limb is permeable to solutes, so they can leave the ascending limb, but it's not permeable to water. So this represents one of the epithelial cells in the wall of the ascending limb of the loop of Henle. And we have on the apical membrane that's facing the filtrate or the urine, we have secondary active transport going on. So sodium is going to flow down its gradient into the cell, and that'll pull the potassium and chloride ions up their gradients into the cell. We also have a sodium-potassium pump that's on the basolateral membrane, and that's what's going to make it possible to do the secondary active transport on the apical membrane. So it'll keep the sodium low inside the cell. And so once the sodium gets in the cell, it gets pumped out, and then the potassium will go through a leak channel along with the chloride ions. And so all of these solutes leaving and entering the renal medulla, along with the urea, which is a waste product made from breaking down proteins, those are all the solutes that are going to create this medullary osmotic gradient in the renal medulla. So if you look how osmolarity is calculated, you can see it's the number of solute particles divided by the volume. So if you're putting a lot more solute particles out here in the renal medulla, that's going to increase the osmolarity. And if we take a look at the filtrate, what's on its way to becoming urine here, you can see that at the bottom of the loop of Henle, the filtrate is really concentrated. So it's at 1400 milliosmolar, which means it has lots of solute in there. So lots of sodium and chloride ions and potassium. And as it turns the corner here and goes up, because these cells are permeable to the solutes, we have lots of solutes to move out into the renal medulla. And as you go further up, as you move those solutes out, that's going to decrease the osmolarity of the filtrate because you're moving those solute particles out into the renal medulla, and now you have less solute in the filtrate, what's becoming the urine, and so the osmolarity will decrease. So by the time you get up to the distal convoluted tubule, the osmolarity of the filtrate is at 100 milliosmolar, so it's actually very dilute, and if you were to urinate that out, it would be really clear and hardly yellow at all because it's really dilute and there's not a lot of solutes in there. So that's the ascending limb of the loop of Henle. So permeable to solutes, we can move the solutes out from the filtrate into the renal medulla and create this medullary osmotic gradient. So we've got a lot more solutes at the bottom of the renal medulla near the renal pelvis, and then as we get up towards the renal cortex, we don't have quite as much solute as we go up each layer here. So that's our medullary osmotic gradient that we've created. And that medullary osmotic gradient is very important because that's going to allow us to concentrate the urine, so to reabsorb water out of the urine in the distal convoluted tubule and collecting duct. Let's take a look at the descending limb of the loop of Henle and these juxtamedullary nephrons next. So these are just the opposite of the ascending limb. So the ascending limb is permeable to solutes but not water. The descending limb is going to be permeable to water but not solutes. So let's take a look at a picture here. So here's our descending limb of the loop of Henle and these juxtamedullary nephrons. And it's going to be permeable to water, but not solutes. So as the filtrate comes down through this descending limb, our osmolarity is at 300 milliosmolar. And then we hit our next level here in our renal medulla, and the renal medulla is at 500 milliosmolar. So because it's permeable to water, remember water likes to follow the solutes. So water says, hey, there's lots more solutes out here, where it's 500 milliosmolar than in here in the filtrate where it's 300 milliosmolar. So the water will leave, and as we go down to the next level, the water leaves till we get the 500 milliosmolar at that level, and then we get to the next level where now it's 700 milliosmolar outside. So more water will go out towards more of the solutes there, and that will happen until we get 700 milliosmolar at this level of the filtrate. And then we go to the next one and we just keep reabsorbing more and more water. And as the water leaves, we're going to decrease the volume in our osmolarity formula here. And if you decrease the volume, that's going to increase the osmolarity. So we're reabsorbing water here, leaving the solutes in the filtrate, and by the time you get down here at the bottom, the filtrate is highly concentrated with lots of solute particles, so it's at 1400 milliosmolar. This water that we're moving out of the descending limb, that's going to be reabsorbed and put into the blood, and we end up reabsorbing about 15% of the water from the filtrate through the descending limb of the loop of Henle. But remember that the majority of the water is going to be reabsorbed by the proximal convoluted tubule. Remember that's going to reabsorb 65% of the water. So 65% of the water in proximal convoluted tubule absorbed, and then the descending limb, we're going to reabsorb 15% of the water there. So the importance of this descending limb is because we're reabsorbing the water, we get, by the time we're at the bottom here, very highly concentrated lots of solutes in the filtrate, and that's perfect for when we turn the corner. Of go up the ascending limb that's now permeable to solutes but not water. And so now we can move all of those solutes out into the renal medulla, and those solutes will create that medullary osmotic gradient in the renal medulla. And this is just some pictures from your book, just showing how the medullary osmotic gradient is going to be created. So as the filtrate flows down, and we have the different permeabilities, so the ascending limb is going to be permeable to the solutes, but not the water. Solutes move out. That'll increase the osmolarity of the renal medulla. And then as the filtrate keeps moving through, and then also showing the descending limb permeable to water but not solutes, so that'll concentrate and increase the solute concentration here of the filtrate. And then you finally end up with your medullary osmotic gradient here in the renal medulla. The loop of Henle, very important to remember that it's called the countercurrent multiplier. And it's called that because as you go down the renal medulla, the osmolarity gets higher and higher, so it multiplies as it goes down. So that's how the loop of Henle and these juxtamedullary nephrons got the name countercurrent multipliers. So make sure you remember that for the exam. It's called countercurrent because counter means opposite and current's talking about the flow, because the filtrate will flow down and then on the other side it will flow the opposite direction. So that's where countercurrent came from. And this is just a overall picture of creating the medullary osmotic gradient. So remember the descending limb permeable to water, but not solutes. So we reabsorb about 15% of the water from the filtrate. That'll highly concentrate the solutes inside the filtrate. So now we're down at 1400 milliosmolar. And then when we turn the corner and go up the ascending limb, that's permeable to solutes, but not water. And so we move the solutes out of the filtrate, and along with some urea from the collecting duct, all of those solutes are going to create this medullary osmotic gradient here. And then by the time the filtrate gets up to the distal convoluted tubule, we've removed a lot of the solutes, and so now it's very dilute at 100 milliosmolar. And the renal medullary osmotic gradient, remember, is really important because that's what's going to allow us to do our final concentration of the urine in the distal convoluted tubule and the collecting duct. So this is just a summary of the loop of Henle from that juxtamedullary nephron, also called the countercurrent multiplier. So we're just going to concentrate the filtrate in the descending limb of the loop of Henle because we're going to lose the water, reabsorb that, but the solutes can't go out of the filtrate. And then the filtrate will be diluted in the ascending limb as it goes up because solutes are going to move out, but it's not permeable to water. And this will create our medullary osmotic gradient. The Vasa recta, remember these are the capillaries in the juxtamedullary nephrons. So we go from the afferent arteriole into the glomerulus, that capillary bed there, and then we exit through the efferent arteriole, and then we go into these peritubular capillaries. The peritubular capillaries will also extend down along the loop of Henle, but because they straighten out, because that loop of Henle is so long, they call it the Vasa recta. So Vasa is just talking about blood vessel, recta means straight. And we're going to take a look at how the Vasa recta works, and the Vasa recta is called the countercurrent exchanger. So in our picture, we've got our loop of Henle here on the inside, and then on the outside here we've got the Vasa recta. So that's our blood vessel that's going down and following around the loop of Henle. So as we come down the Vasa recta, you can see that the blood osmolarity is at 300 milliosmolar. And the Vasa recta is going to be permeable to both water and solutes. And that's going to be the same on both the descending part and the ascending part. So they're both permeable to water and solutes at the same time. So as the blood comes down, 300 milliosmolar, it's going to hit this renal medulla where the osmolarity is 500 milliosmolar. So as the 300 milliosmolar comes down to where it's 500 milliosmolar, water is going to leave the blood because it wants to follow the solutes, and there's more solutes out here where it's at 500 milliosmolar. So water will leave, but the solutes, like the sodium chloride, are going to move into the blood because they're going to go from high solute concentration out here at 500 to much lower solute concentration inside the blood at 300. So water moves out, salt moves in until the osmolarity is at 500 milliosmolar in the blood. And then the blood moves down to the next level in the renal medulla where now it's 700 milliosmolar. And the same thing will happen. Water is going to move out and sodium chloride will move in. So by the time we get down here to the bottom, the blood will be very concentrated, lots of solutes in there, and not as much water because we've reabsorbed some of that. So with the Vasa recta, we've actually been stealing the solutes. So we're stealing all this sodium chloride and other solutes. We're taking that away out of the renal medulla. And remember, those solutes are really important to create this renal medullary osmotic gradient. So what we want to do is we want to return the solutes when we go around the other side. Because if the Vasa recta just took off and went to the renal vein right here, we would take away all of those solute particles and eventually the medullary osmotic gradient would be gone. So as we turn the corner and go up back towards the renal cortex, we're going to return the solutes to the renal medulla. So as our blood flows to our next level here, so this next level we're at 1200 milliosmolar, and here we're at 1375 in the blood. So remember that water likes to follow the solutes, so it's going to go into the blood because the osmolarity is higher at 1375 there. And then the solutes are going to go out because they're just going to go down their concentration gradient. So they're just going to go from 1375 out to the 1200. And then the osmolarity of the blood will be 1200 milliosmolar, and then you get to the next level and you do the same thing. So you're going to move the water back into the blood and move the solutes out into the renal medulla. So as you do this, you will take water back into the blood and put the solutes back into the renal medulla. And this will return the solutes that you stole as you went down the renal medulla. You put them back on the other side as you go up the other side to the renal cortex. So this is why the Vasa recta is called the countercurrent exchanger. So countercurrent, just talking about how the blood flows in opposite directions. It goes down on one side and up on the other. And it's an exchanger because it steals the salt on one side as it goes down, but as it goes up the other side, it puts the salt back. So the Vasa recta is the countercurrent exchanger, and the loop of Henle is the countercurrent multiplier. So don't get those two confused. Those are really important to know. And then this is just a summary of the Vasa recta, just showing you the blood flowing down towards the bottom of the renal medulla and then coming back up on the other side. And note that the Vasa recta is going to be permeable to both water and solutes. So as we go down, we're going to steal the solutes. They're going to go into the blood and we'll put the water out. But then as we go up the other side, we're going to put the solutes back. So that way we're not going to get rid of our medullary osmotic gradient that our loop of Henle worked really hard to establish.